Okay, we'll move on here to number 11. Number 11 starts talking a little bit about models and modeling. So we're given the model A equals 246 e to the 0.035 t. Now, just looking at this model, we should be able to pull out a couple of pieces. For example, this general form is the amount equals a naught e to the kt. That a naught, a sub 0, is amount at time 0. So whatever this is modeling, it started with 246. And this k, let's just label this start amount. And that k is the growth constant. Or you can think of it as the rate if you want. So we started at 246. We're growing with a positive constant, so we're actually growing as opposed to decaying. If this is negative, our growth is negative, we'd be shrinking. So you'll see sometimes this is negative when you have something that's either decaying or a population that's shrinking, or so forth. So it models a population of fish in a lake T years after 2005. So I'm going to write that down. T years after 2005. Calculate the year when the population is 6,800. So find T for A equals 6,800. Okay, so it's nice. We just let A equal 6,800. So 6,800 equals 246 e to the 0.035 t. And we just have to solve that. So again, just like one of the other ones here, we have, this is where the complicated stuff is going on, so we want to isolate it. So I'm going to get rid of that 246. It's attached by multiplication, so we divide it off. Divide by 246, and then we could reduce that or turn it into a decimal. The key is, how do we handle this e to the power? Well, you get rid of e to the powers, you get rid of any exponentials with logarithms. This is an exponential based e, so log base e would certainly be the most natural choice. Again, the one I gave you online uses a slightly less, in my opinion, happy notation, but I want you guys to see some different looks at it. So don't know what the natural log of all of that is. I know we could reduce that some, but eventually we're going to get a decimal approximation for all of this anyway. So I'm inclined to leave it. Your log base e and your exponent base e undo each other. They're inverse functions. That's their job, is to undo each other. I'm going to say that again. The natural log base e, and exponent base e undo each other. Just like multiplying by 2 and dividing by 2 undoes each other. If you have 5 and you add 2 and then subtract 2, you're still at 5. The adding 2 and subtracting 2 undo each other. They're inverse pairs. Natural log base e are meant to undo each other. Just leaving the 0.035 t. Divide both sides by the 0.035, and we have the natural log of, I should at least divide that by 2. What is that? 3,400 over 123 over 0.035 equals t. So this is an exact answer. If we're still interested in exact answers, that's your exact answer. Now this approximates, you get a decimal approximation of that real quick, to something like 95. I think it's 94.8 and change. So that's the time. That's how long it takes. Remember, our t was t years after 2005. So if you take the 2005 and add the 95, you get to the 22nd century. Be sure to answer this in a sentence, something like, it happened in 2100. Okay, make a better sentence than that, but make it actually a sentence. But some sort of sentence that answers that in context, and you're good. The key is, again, we're using that natural log to undo an exponent. Hopefully you're starting to see that as a theme here. Number 12. Use the interest formula in question 2. Find the interest necessary for 3,600, so a principal of 3,600 to grow to 4,500 to turn into amount of 4,500 in 2 years, compounded monthly. So time is 2 years, compounded monthly, so n is 12. And we're asked to find the interest rate. I told you might be expected to find some of these for different combinations. So go back to that, look at that formula, 4,500 equals the principal, 3,600, times 1 plus the rate, we don't know, call it R, divided by 12, raised to the 12 times t is 2. So again, that's A equals P, 1 plus R over N, NT. Again, solving techniques. This is the complicated bit, so we kind of want to isolate it. Get rid of the 3,600. So I'm going to divide both sides by 3,600. So 45 over 36 turns into, was it 9/4? No. 45, how about divide both of them by 9? How about 5/4? Okay. Equals, those undo each other. 1 plus R over 12 to the 24th power. Now this 24 is a power, not an exponent. It's a power because it's a constant, it's a number. If it had a variable in it, if it was like 12t, that would be an exponential. We'd have to use a logarithm. But this is just a constant. We don't need a logarithm to undo a constant power. How do you get rid of something to the 24th power? Well, if this was just squared, you'd take the square root. If it was to the third, you'd take the third root. It's to the 24th power, so yeah, you take the 24th root. So the 24th root of 5/4 equals 1 plus R over 12. You might have thought, I'm never going to use higher index roots. People who work with money do it all the time. So then we're going to subtract the 1, subtract the 1. So the 24th root of 5/4 minus 1 equals R over 12. Multiply both sides by the 12. 12 times the 24th root of 5/4 minus 1 equals R. And again, that's an exact answer. It's a nice exact answer. Now, if you want to go with decimals along the way, just carry a few more than you'll need. But again, you should be able to work exactly. Then once you're done, you can say, hey, okay, what's that thing's decimal approximation? And you'll find it's 11.2%. And by the way, if you find an investment that pays out 11.2%, let me know. Or don't trust them because it's probably the mafia. Not that the mafia exists. Anyway, so you should be able to solve those for R, for N, for A, for P. The only ones that require logarithms at all are solving for either N or T. The most common one is T, because we're solving for the ones in the exponents. If you're not solving for something in the exponents, you should never need logarithms. Here, that exponent was just a constant, so we were able to use the roots instead of logarithms. That's the distinction there. If this was just 2t, we couldn't take the teeth root. Teeth root doesn't do anything for us. Hence our need for logarithms. Okay. So that was 12. Let's look at 13 here. So again, back to that interest formula and find the time necessary. So again, number 13, this is what I was saying just a moment ago. Find the time necessary to start with 4,600, end up with an amount equal to 8,800, compounding daily, n equals 365. Rate, we have to be told the rate there somewhere. The rate is 6.9%. And we're asked to find what's t. So set up the relationship. So 8,800 is the ending amount we want with a principal of 4,600. Really? Okay, fine. 1 plus 0.069, make sure to always use that in decimal form, over 365, raised to the power 365t. We want to solve for that t. As soon as you see what you're solving for is in an exponent, you should be thinking, I'm going to need a logarithm to handle that. Just like the fact that these are multiplied together, you know eventually you're going to have to divide by 365. That should have become intuitive by this point. You want to get your intuition to go, hey, this is in an exponent. What I'm solving for is an exponent. I'm going to have to use a logarithm eventually. So how do we do that? Again, first isolate the thing that has the exponent on it. So divide that 4,600 out of the way. Divide the 4,600. Let those zeros cancel. Divide both those by 2. So 44 over 23 equals 1 plus 0.069 over 365 to the 365t. Oh, I suppose we could add those together. So that turns into 365 over 365 to get common denominators. So 365.069 over 365. I wouldn't blame you for turning that into a decimal, by the way. I probably will in a second here. I know I really like staying exact, but this is just a little silly. So let's go ahead and turn both of those into decimals. So 1.9 equals 1.000189 to the 365t. Now notice I kept this very, very accurate. This less accurate. Exponents are very, very, very touchy. And you want to add, say, 1, 3 onto that, great. But exponents are very touchy. So this number, the base of an exponent, should be very accurate. Very, very small fluctuations make huge, huge changes in your output. So carry many more decimals than you think you need. Round when you're done. It makes a huge difference, which is hence me stressing, be sure to use exact values when you can. So, it would be very much safer to just stay with the fractions. But I'm digressing there. So, how do we get access to the exponents? Well, logarithms, and we can use any logarithm we want. Natural logarithms, I think, are the most natural, but common log would do as well. You could use log base 1.000189 if you wanted to, but you can imagine that makes a mess. And again, the idea of using the logarithm is it gives you access to the power property. That allows us to bring our variable down from being an exponent to being just a product. So in the natural log of 1.913 equaling 365 t times the natural log of 1.000189. Now that t is just being multiplied by those. So to get rid of them, we can just divide. And we get the ability to do that, divided by both sides, we get the ability to do that from the power property because we have a logarithm. So we're left with t equals the natural log of 1.913 over 365 times the natural log of 1.000189. And we'll be able to get an approximation from that. I think it's something like 9.4. So again, answering a sentence, it will take about 9.4 years. You write yourself a nice little sentence. But notice the process is very similar to the other ones. You set up your relationship, isolate your exponential, use logarithms to either get rid of the base if it's base e, or to give you access to the power property. Once you have access to the power property, it's just division. So practice those, lots of those. You'll do a lot of those in your chemistry stuff and your physics stuff and your biology or your economics or your sociology for growth or your zoology and biology for population models, your chemistry for molecular decay. These exponential models are very, very common. Anytime you have a model that's exponential, you will need logarithms to solve it. One does not get away from logarithms. Okay, 14. Oh, and for those of you who are going on a calculus, they come up a lot. So, yeah, it never goes away. So, in 14, looks like we're given a logistic function here. 14.64 over 1 plus 5.9 e to the negative 0.36, 0.36 t. Now, logistic functions, as you know from your reading, have a carrying capacity, so that 14.64 is your population's carrying capacity. So if we were to graph this, it would grow exponentially for a while and then level off. That leveling off point is your carrying capacity. It's when your environment, like say this was a growing population, it's when the environment runs out of food or space to grow anymore and it levels off to an equilibrium point. We're doing here world population in billions, where t is time after 1952. So if this model was made in 1952, I don't know when this model was made actually, but when this model is made, we have the resources and technology for the planet to handle 14.64 billion people. It's about almost twice, more than twice what we have now. We keep pushing that carrying capacity up a little bit and a little bit by advances in technology, but we're not doing it as fast as we're growing yet. So stop breeding. Sorry. So be careful about how much you breed. So calculate the year the population will reach 9.8 billion. So if this models the population, we want to know when does this equal 9.8 billion. So set it equal to 9.8. A lot of people get a little intimidated by this form of logistic functions. They kind of just stare at them and go, oh, well, what do I do? Anytime what you're trying to solve for is in a denominator, denominators cause trouble. Get it out of the denominator. Well, how do we get this out of the denominator? Multiply it on both sides. So multiply this side by the 1.1 plus 5.9 e to the stuff. Multiply this side by the 1 plus 5.9 e to the stuff. I know I'm being very technical with my stuff there. But those are going to cancel out. And you're going to end up with 9.8 times 1 plus 5.9 e to the negative 0.36 t equals 14.64. As soon as people get in this form, they're generally more comfortable. You kind of know how to handle something from this in this form. That 9.8 has to go away, so divide it. 1 plus 5.9 e to the negative 0.36 t equals 14.64 divided by 9.8. Get a number for that. 1 plus 5.9 e to the negative 0.36t equals whatever that value is. Do I know what that value is? Can I look that up? Oh, can I do it? 1.494. Or you want to be super accurate, stay in exact. Subtract the 1, subtract the 1. Again, we're trying to isolate the exponential part. So 5.9 e to the negative 0.36t equals, subtract the 1, 0.494. Divide the 5.9, divide the 5.9. Again, we're trying to isolate the e to a power. Try to isolate what you're trying to fix. Let's see, do I know that division? 0.0837. 0.0837. Now that we have it isolated, how are we going to get access to that exponent? Well, the way you undo something being in an exponent is with a logarithm. Because those are both base e, they will undo each other. If not, you could use the power property too. Bring out and down that negative 0.36t and multiply it by the natural log of e, but the natural log of e is just 1, so you end up with this either way. So if you don't like the whole, keeping track of the fact that the natural log and the e undo each other, because they're inverse functions and that's how they're defined, I mean, that's the whole point. But if all you know is I'm supposed to bring that down, and then you take the natural log of e turns into a 1, you end up with this anyway. So, whatever floats your boat equals the natural log of 0.0837. Still trying to solve for that t, so getting squishy down here. Divide by the 0.36, divide by the negative 0.36. So we end up with a nice t equals the natural log of 0.0837, which is going to be negative by its nature, divided by the negative, so the whole thing will turn positive, 0.36, and we end up somewhere around 70. So things are ever so slightly less than 70, 70-ish. Since t is time since 1952, add 1952 plus 70 years is going to be 22, and it's a little bit less than 70, so it'll happen just before 2022, so it'll technically happen in 2021. Is that what Doug got? Let me check. Yeah, so this is 68.9, so it happens 68.9, so it happens at 21.9. No, 20.9. So it happens sometime during 2021. So during 2021, the population will reach 9.8 billion. And of course, you write a little sentence. It will happen in 2021. So careful about overpopulation. Okay. Well, I'm way over time. Let me stop that video and we'll finish up with just one more.